In this video, I'm going to be talking about the first lesson in the particles and energy scheme and how best to teach it. So this lesson is called What is Science? And it's a lesson which is very easy to skip over because it kind of isn't really in the national curriculum. It seems like it's a bit abstract and maybe not relevant to a lot of what the students study. But I would say this is the most important lesson in the whole curriculum in many ways, because it sets up the model that we're going to give to students for them to understand what scientists do when they create their knowledge. I think students have some idea of what science is. It's this kind of body of knowledge, they think, which tells us all about the world. But what they don't have a sense of is, if you are a person who describes yourself as a scientist, what is the process by which you go about your business, and how is that different to what a historian does or what a poet does or whoever else? Because I think it's really important that they understand those differences, so they get a broader sense of the knowledge that these disciplines have created. So rather than going into lots of philosophy of science straight away with a load of Year 7 students, the way I like to introduce this is with almost like a little game, the mystery boxes activity. So I've prepared a little box here, which hopefully you can see. Now, I was just trying to find a box at home, and I've got my son's Paw Patrol money box. Now, when you do this in class, something like this maybe isn't the best. You certainly don't want a hole in the top. If you can padlock it or just sellotape it or something like that. What's really important is that the box that you use is sealed. And the reason for this is because the model of science that I present to students is we have the world around us. There's this whole world that we're familiar with. And there's lots of things that we can see happening. I don't know, the sunrise in the morning, volcanoes exploding, so on and so forth, chemical reactions taking place. We can see all of these things. What science does is explains why these things happen in terms of things that we can't see. And the mystery boxes is a really nice example of this. Maybe I'll hold it up here. It's a really nice example of this because the idea is, well, we can't see what's inside the box, but by thinking about it in a certain way, we can work out what actually is inside the box. So the first thing that we do when we're thinking about this, and in the lesson resources, there's a lovely video of Richard Feynman talking about this, but the first thing that we do is guess. So we just have a guess. So I'm going to start here. I've got a money box here. So I'm going to guess, well, okay, it's a money box. I'm going to guess there's a coin inside. That's our mystery object. What we have to do next is think, okay, if there was a coin inside, what would I expect to happen? We need to deduce the consequences. And before I do this, I might draw this, and I would draw this to students and get them to draw it in their book as well, so they've got an idea of the model. Let's do it. So I'm going to write guess under here. So this is the first stage by which scientists generate knowledge. As we'll see, you can see lots and lots of examples of this throughout the history of science. These are the models with which scientists try and make sense of what's going on. So I'm going to sketch my box here, my mystery box, like this. And I'm going to guess, because it's a money box, that there's a coin inside. Okay? And I might want to label that as coin, like this. So then we have to deduce the consequences. Okay, if my guess is correct, what would I expect to happen? I need to generate some sort of testable hypothesis that I can then do an experiment about to confirm whether my guess is true or not. So in this case, I'm going to say, well, okay, if this was a coin and I were to tip my box, and students will be, they will be shaking this about and feeling the weight of it and trying to work out what's going on when you let them loose with this. But what we need them to understand is, if you're really thinking about this systematically, you want to say, well, okay, if I were to tip it like this, if my guess was correct, then what I'd expect is it would slide down like this, and I would hear a kind of sliding sound. Now, I don't know how you draw a sliding sound. The picture isn't as important as the logic, so I'm going to write sliding sound like this. And maybe a few arrows to show this is moved within the box. Okay. Now I call this stage deducing. and this is a hard word, but I think it's a really nice word because deduction is what science, or is a lot of what science is all about. And I like to give them this idea that scientists are detectives, and they might have heard, if they've ever read any kind of crime stories or anything like that, this idea of making deductions. Well, this is exactly what scientists are doing. They're trying to solve a puzzle using lots of clues. So they deduce, if my guess was correct, and I tipped the box up, then I would expect to hear this sliding sound. And then the last thing that scientists do, and this is what really sets science apart, and again, Feynman's video captures this beautifully, what scientists do is check it. They say, well, okay, if I actually do tip the box, do I hear a sliding sound? So I'm going to do it like this. So if I tip the box, oh, other way. Yeah, I kind of hear that sliding sound. Okay, so in this case, I did have a coin in there. I can show you guys. Obviously, you don't show the students because you want them to see. You want them to get the idea that in nature we can't open the box. We can't see these invisible things like atoms or other things. We have to work it out. So what I'm going to do, and I need to hide this so that you guys can't see, I'm going to put another mystery object in. So now, okay, let's say I've made my guess that it's a coin, and I've deduced what would I expect to happen, and that's really important language that I suggest you use with your students. What would I expect to happen if my guess was correct? Well, if I tipped it up, then I'd hear a sliding sound. So I've put a different object in here. Now I'm going to check whether my guess is correct. Oh, can you hear that? So I hear a sliding sound, but actually, don't know whether that's audible on the laptop. That noise that it makes when the object hits the side, it doesn't sound like a coin. So maybe I should add another deduction here, a kind of metallic bump. And again, I'm not sure what language you would want to use with your students, but hopefully they'll get the idea. Now in this case, when I've done that, I got a bit of a sliding sound, but I didn't get the metallic bump. Let's try it again. I've got a softer bump. So what this is telling me is that when I've done this check, my guess that it was a coin was not correct because I didn't get the metallic bump. And I might illustrate this with a red cross or something like this. Now what we've got to do here is say, okay, if we make a guess, we deduce what we'd expect to happen, and then we check, and it doesn't confirm our guess was true, well, what we need to do is come up with a new guess. So I got a kind of softer bumping sound. I'll leave you to have a guess maybe. You can have a think. What do you think I put inside the box? Students will love this, by the way. So now I'm going to guess, okay, maybe a lump of blue tack. Maybe there's a lump of blue tack inside the box. Because that would make that kind of soft sound like this. Blue tack. I never know how to spell that word. I'm just going to write it like that. Blue tack. Now, again, you can go through that process again. Well, okay, if my guess was correct, well then actually I'd expect to hear a rolling sound when I tipped it up. So I would go like this. When I tip it up like that, I would expect it to make that soft bump. Like this, soft bump, but I might hear a kind of rolling sound as it hits the bottom. So then I do my check again, and I'm labouring the point here for the sake of this video, but hopefully you'll see. Actually, no, it doesn't seem to make a rolling sound, it makes a sliding sound. So I'm going to need a new guess again. Now the point here is, this is how scientists generate knowledge. And again, this all might seem a little bit arbitrary, but we want to give students a model, something quite tangible that they can get their head around, before we start introducing this in terms of real examples. Now there's lots and lots of examples, and throughout the Key Stage 3 curriculum, in every scheme of work, I come back to an example where we use this kind of guess, deduce, check model. I just want to show you the classic example here, which is models of the atom. So Dalton was the first person that we talk about to make this guess. He guessed that atoms were these hard spheres, and he said they were indivisible. If atoms were hard spheres, what he would expect is that there would be no smaller particles. Now, actually what Thomson found out, and this was the check that disproved Dalton's theory, was that there were these extra particles called electrons. So then, as I'm sure you know, we needed a new guess. So Thomson made this guess, well, okay, they must be hard spheres, and the electrons must be kind of scattered randomly through them. But then Geiger and Marsden do this experiment. Now, if Thomson's guess was true, well, you'd expect all of these alpha particles to go straight through, because nowhere in this plum pudding model is mass and charge concentrated enough to repel those super high energy alpha particles. But when we checked what actually happened, and I'll move this up so you guys can see, well, as I'm sure you're aware, some of them bounced back. So this is why Rutherford realized he needed a new guess. And this is how we came up with the nuclear model, and so on and so forth. The point here is, when we teach that, quite often what I see is in year 9, we come to that part of the course and we just tell them, well, you know, obviously we'd expect all of them to go straight through the plum pudding model, but they didn't, so that's why we need the nuclear model. And we kind of bring in all of this really complicated, difficult disciplinary knowledge about the nature of scientific truth, and we kind of throw it at them in a 50-minute lesson and expect them to remember it. And actually, what we need to do throughout this curriculum, and the reason I put this lesson at the very, very beginning of year 7, we need to give them a model to help them understand what it is that scientists are doing, so that when they get to that point, they have a sense of, okay, I've seen this before, this is not something that's unusual to me. So, hopefully that gives you an idea of how you would run the mystery boxes lesson, and the kind of diagrams you might draw in your book, or students might draw in their books as well. The next lesson we'll look at the particle model, one of the first guesses, in fact the first guess that we're really going to come across within the science curriculum. Thank you.